All right, well, thanks for joining today. I'm Mark Scarpness with Intel, and happy to share with you a little more detail of how we work in the Linux upstream and how we're working with SUSE. If you were in the keynote this morning, I touched on it just a little bit, so we'll talk in more detail about the overall process and how we think about open source. If you have any questions on any of the details, happy to cover that. I'll talk a little bit more about confidential computing and AI as well. It's interesting if you think about the theme of the conference around choice and open. Those are core tenets of Intel as well. Open, choice, trust. We've been working in open ecosystems really forever. That's always been a foundation of Intel, working in horizontal open ecosystems, whether that's in open standards or in open source, open hardware platforms, open APIs. I've been working at Intel for more than 30 years, and I've worked in and around open source for most of that time. We were involved in Linux in the very, very early days, and working with the Linux ecosystem. You can see a few stats on the bottom. I'll touch on a few of these later on. We have very broad contribution across the open ecosystem, very active in Linux kernel. We've been the #1 overall corporate contributor for many years. Also a big contributor to Kubernetes. We're one of the top 10 contributors. And many, many other projects. So we have a long history of building open ecosystems and participating in them actively, and I'll talk in a little more detail about some of that. And this is just to further that point. If you look at where we participate across that ecosystem, really from the bottom in the foundational software layers, and we'll talk more about our partnership with SUSE today, all the way through the stack. At every layer of the open ecosystem, we're participating, contributing to open source projects, creating new open source projects. So I'm not going to talk about the eye chart of all the projects, but we're very broadly participating. And many times working on making sure that the combination of our platforms and the open source software works well together. And I'll talk a bit more about that. So in terms of how we do this, sort of from a method point of view, and this is something we've been doing for a long time, especially as we're building new hardware platforms, we're thinking about what are the new capabilities, the new features, whether that's AI acceleration or new security capabilities, new performance features, new instruction sets. We start very early on in something we call tech readiness, where we're thinking about, hey, there's a new feature we might bring out. What is its impact to software? We'll go talk to key players in the open source community. So we have a very long-standing relationship with Linus Torvalds and some of the key upstream maintainers, and we'll bring early hardware concepts to them and say, hey, what do you think of this? And Linus is not a shy guy, if you've seen Linus talk. So sometimes he'll tell us we're nuts and we shouldn't do that. And other times, he's like, hey, that's a great idea, or have you thought about this or thought about that? And that's a really important part of the process for us to think carefully about how is this new feature going to land in the software ecosystem. Is this going to be easily integratable? Is it going to be hard to integrate? We don't always get it right. I think it's been a learning process for us, especially with some of the more complex features, but that early feedback is really important. And we'll do that with key partners as well. We'll talk to SUSE, we'll talk to other folks in the open ecosystem to understand, like, what do they think of this? Is this really going to bring the value that we hope it will bring? But once we sort of figured out, hey, we're going to build this, as you can imagine, building a new server platform is a pretty long journey. It's 4 years probably from the beginning of this to when something launches, on average, something along those lines. So we're doing this internal work of starting to build early prototype code. We're building silicon at the same time, and we're getting ready for sort of a key moment for us, as you can see on the right, is we have a new platform and we've written all the code and we've tested it on simulation, but we haven't pushed it externally into open source projects yet. We power the platform on and we test it. Like, does this pre-silicon code actually work on the platform? So that right before that green box, we're going through this last validation step. Does everything look right? Is this ready for us to share with the community? So sort of our first exposure of this code typically to the upstream, like kernel, for example, is once we're confident that the code is functionally correct, like it works on the platform. That's not the end of the journey in upstream, that's the very beginning. Like, we'll post the first, say, RFC code or first set of patches on the Linux kernel mailing list, and depending on the complexity of the feature, we've gone down this journey of Maybe it's one kernel cycle, maybe it's 2 or 3 years, depending on how complicated and invasive the architecture is. But that's the general process, and it's true for compilers. So we work in GCC and LLVM doing something very similar with new instruction sets. There we oftentimes start even earlier because there's not as much dependency on the details of the implementation to make sure that it's correct. We know, like, this is the instruction set, here's how it behaves, we've written a spec for it. We're doing upstream work on some new instructions that aren't coming in hardware for another few years. We've been merging that code in GCC in the last 6 months for something called APX, which brings new register sets to x86. That code's already in the compiler, even though you won't see it in a platform for some time. Because it takes a long, long time for the ecosystem to absorb new compiler version, and then everyone has to take advantage of it, recompiling. So doing this as early as possible, I think that's the other lesson we've learned over the years, is the sooner we can start this work and get the code flowing, the sooner it'll get into your hands so you can actually take advantage of it, because it does sometimes take a long time. So we're ultimately trying to get our work upstream. That is the path to scale for everything for us. So our goal is always land it upstream and then work with the downstream ecosystem to get it integrated into all the products. So a little bit more on upstream, and this is sometimes a very challenging process. We've learned a lot in working in upstream through the years, through doing things wrong, having the wrong objectives. If you put yourselves in the seat of a Linux kernel maintainer and you think about the workload in the Linux kernel, there's a new Linux kernel version about every 3 months, and it typically has about 10,000 changes in it. And there's only maybe 30 to 50 people at the top of, you have Linus, and then you have all the subsystem maintainers under Linus. Their workload is crazy. The amount of code they have to look at and decide, am I taking it, am I not taking it? It's really a lot of work. And they're responsible for making sure they don't break the kernel. You can imagine Linux is running on 5 billion devices today, probably something like that. If you think about phones and embedded devices and the entire infrastructure of the internet and you name it, everything is running Linux. That responsibility burden is really high. So correspondingly, the bar they set for taking stuff, especially things that are changing common code, is really, really high, as it should be. Because if they take something that breaks the kernel, that's bad. That's going to probably be in the front cover of a lot of newspapers if they broke it in a meaningful way. So they take it very seriously. And so we spend a lot of time, we have a large number of kernel maintainers at Intel. So we do an internal review process very early on, do an architectural review process, and really do our best to engage with the community as members of the community, putting ourselves in that, think like a maintainer mindset. What would we do for maintainability, for long life support? Because the other thing with kernel changes is they're around a long time. If you as a maintainer merge code into the kernel, it's going to be there for decades. So you need to make sure that it's right and it's maintainable and it's going to stand the test of time. So this is a continual process of learning how to be good community citizens and how to get our code accepted in the right way. And sometimes that means it takes longer. We'll talk about confidential computing and TDX. Confidential compute infrastructure in the kernel is really, really complex. And we've been working on merging it for 2.5 years now. And we still probably have another year to go before we'll get the first full set of it. Same with other architectures. There's a whole exercise of merging across hardware architectures, what's the common infrastructure for confidential computing, because you don't want to have 3 copies of that in the kernel. That would be really bad from a maintainer point of view. So you want one common foundation and then hardware-specific code on top. So it sometimes takes quite a long time to get this finished. But it's essential, because if you get it wrong, you're going to end up doing it again. We've learned that lesson also. If you build some infrastructure that's not quite right, it's going to end up having to be reworked because it won't meet these criteria, it won't stand the test of time in the kernel. And this is true in other projects as well. I think that general philosophy of common architecture, reuse, maintainability is key to being successful. And these are just, as I said, we've been a kernel contributor forever, and generally the biggest corporate contributor. And the blue line is the Intel contributions. We track it. There's LWN does a regular kernel report and we pull from that. This is a little bit zoomed in, so this is like over the last, I don't know, couple of decades probably, and this is recently. You can see it kind of ebbs and flows depending on what's going on in new technology, but we're generally very, very active kernel contributor, pushing new code for our new platforms and helping to get that integrated. So that's the front end of the process, the left side. And then there's, how do I get it into a product? So we've been talking a lot at SUSECon about the work we do with SUSE. You can see them there in the middle, working to get our code from the upstream integrated into product. So we do co-engineering, we do regular engineering meetings, we make joint plans about, hey, we have this capability coming, it's going to be in that upstream, and we line up releases and plan together how are we going to get that code integrated into Linux distribution products. We help do validation, we help do backporting in some cases, and we work across lots and lots of ecosystem partners. All of the usual suspects. There are many Linux distributions. All the CSPs have their own Linux distributions these days. The ecosystem in China has their own unique ecosystem now with their own purpose-built Linux distributions. So that process is going on with a number of these different communities, very similar in principle of here's what's coming in the platform, here's where the code is going to land in the upstream and when it's going to be ready, and how do we plan out when that can land in a product, and working to get that out and verified and ready to go into use. So that's kind of the upstream work, and then into the downstream. And I'll talk a bit more about what we're doing specifically with SUSE. So we've been working forever with SUSE since they were first formed, and we have a very regular co-engineering activity. Foundationally, we want to make sure, hey, we've got a new Xeon platform coming out, like we just launched our Xeon 6 eCore product a few weeks ago, and we've lined that up so it's supported in the latest SUSE Linux releases, and I'll talk a bit about the timing of all of that. But getting the foundational platform support in place across server and edge and client, so that when you buy one of those platforms and you take a SUSE Linux version, it just works. That's goal, kind of foundational goal, is everything should just work. Both latest version, and typically we're also doing N-1, because people obviously are not all running the latest version. So we're trying to get at least foundational support in what's most broadly deployed, and maybe for the latest features you may have to have a new version in some cases. But getting that core certification ready across the operating system vendors and the OEMs, ready to go out of the box at days. The goal is day 0 of launch of a new platform, you should be able to run SUSE Linux, and it should work great. You should get good performance and have access to the new features. And then there's specific focus areas. And I'll talk a little bit more about AI, which is, of course, very hot these days. Security. Performance is another one we've been working on. One of the interesting things if you look at x86, we've had an evolution of the instruction set over the last 20 years. We're now at ISA version 5, I think, or 6. Most of the Linux distributions in the world, especially enterprise, are built for very, very old ISAs, because those run on everything, 20-year-old hardware. But you're leaving a lot of performance behind when you do that. So we're working to get more modern ISA support into the Linux distributions so that you can take advantage of all the latest performance. And it's a trade-off between compatibility and performance, so it's kind of a slow journey. But there is 5 to 10% performance typically available, depending on the software, for using the latest ISA. And that continues. We have these new APX that I mentioned, which brings another 16 general purpose registers, another 5% performance. So we're going to keep working at making sure that we get as close as we can to current hardware in the software. And there's OS support. You can also, of course, build applications that use latest ISA, even if the operating system itself isn't built fully to use the latest instruction set architecture. But that's another thing that we do a lot of work on, as well as just general performance tuning. So sometimes there's quirks of a specific microarchitecture that need tuning to get best performance under certain workloads, and we do a fair bit of that analysis and tuning as we need to do as well. And then working on, ultimately this all ends up in a set of products across our roadmap, the SUSE roadmap, and I'll talk a little bit more about that. So this is kind of the details of the latest work, as SP6 has just been announced and launched, you can kind of see where we're at in having server and client support. So the 5th gen Xeon, which was formerly known as Emerald Rapids, that platform is launched and the support's fully available, as well as the 6th gen Xeon. So as I mentioned, we just launched the E-Core flavor of that, which was codenamed Sierra Forest. And if you're into the Intel code names, that's in the Upstreaming platform. So we have 2 processors, Sierra Forest and Granite Rapids. Sierra is the E-Core, Granite Rapids is the P-Core, Performance Core. They both sit in the same server platform called Upstreaming. So Sapphire is supported. And then Xeon, the P-Core flavor will be supported later on as it launches. So it's launching later this year. As there's 2 flavors of that as well. There's a AP, which is the higher end flavor of it, and then the SP, which is more the mainstream, and we'll have support for both of those as they come out on the server side. And then on client, we have our new Core Ultra platform, which Meteor Lake, which launched last year, and that's supported, as well as our discrete graphics, the Intel Arc DG2, which is supported. And then we also have some other sort of adjacency Ethernet cards and IPU and so on, and we have support for that. So you can see we have really good foundational support across the roadmap through the work that we've been doing together with the SUSE engineering team. And a little more, so we not only SUSE Linux, but we also work with the Rancher team and work with SLE Micro. So we're, as you saw earlier, we're very involved in Kubernetes and working with SUSE on making sure that all of our hardware support shows up in Rancher, device plugins and other hardware support. We'll talk more about AI. Granulate is another Intel software. It's got a new name, right? It's Intel Tiber something. You may see it called something else, but they have 2 offers. One is a performance optimization for mostly cloud-hosted workloads, and they also have a Kubernetes sort of workload usage optimization. So this is a software service that lives on top of and can work with Rancher as well. And this is the Kubernetes thing that's with Rancher, I assume, right? All right, so a little more on confidential compute. If you missed Christian's session yesterday, this is a much shorter version of his much longer version on confidential compute. So the new capability, we have ways to protect data at rest with disk encryption, data in flight with network encryption. So the new thing we're bringing with confidential compute and trust domain extensions, or TDX, is how do you protect data in use? And that's coming, currently showing up in our platform roadmap, as well as attestation. How do you prove that the confidential environment is what you think it is and it hasn't been tampered with or modified? And in a little more technical depth, the new thing that shows up in our server platforms first and eventually in the client platforms is something called Trust Domain Extensions, or TDX. And you can see on the right-hand side, we have this new capability of running essentially encrypted VMs. So you can see over here, there's a new layer of hardware and software that isolates these encrypted or trust domain virtual machines from the rest of the software in the platform. So you can see the communication path between the hypervisor in the host OS goes through a new intermediate layer that protects it from any sort of tampering or exposure. So the memory is encrypted. All of the data that's inside of these trust domains is invisible to the rest of the system. So you've essentially isolated the confidential VM from the underlying hypervisor, the underlying host OS. So if you're running this in a cloud context, your trusted VM would be invisible to the CSP. So they wouldn't be able to see what's inside of it. They wouldn't be able to see the memory. Be completely invisible to the CSP. So that would be kind of in the cloud use case, which was sort of the original motivation for doing TDX. Was I don't want to have to trust my cloud hosting provider and have them have the ability to see what's in my VM. Well, with this capability, they no longer can. Like, it's entirely invisible to them. So this is first being deployed in the cloud, but you can also do this. You can imagine edge use cases, as I mentioned this morning, where you might want to do confidential AI in a place where you have a system that other people have access to. You can use the same thing to protect your critical workloads and the data that's inside of them from tampering. Anyone that has access to this side of the platform, the untrusted side, can't see inside of here. This is entirely encrypted by hardware and invisible to the rest of the system. So it gives you that trust boundary that now is leaving out the underlying host OS and the underlying hypervisor. So you don't have to trust it. Yeah. Spectre and Meltdown, you mean? No, not specifically. So you still need the mitigations for those. I mean, you would, for example, you wouldn't be able to go inside of here. Like if you had somehow used a side channel to get access over here, you couldn't get access over there. But if you had something that you would still have to worry about, am I vulnerable inside of here? So it doesn't protect specifically against Spectre and Meltdown, but the isolation between untrusted and trusted would give you a level of protection. Like if you somehow got root access through some attack vector, Spectre or whatever, over here, you still can't see this, right? So the hardware is protecting you against being able to see inside the TDs from the outside. But Spectre itself could apply inside the TD. That we have other mitigations, of course, that we're doing for those that you would have to apply if you wanted to. So they're sort of two different things that kind of intersect in some ways, but yeah. I think we'll be doing Spectre and Meltdown mitigation for forever. This has become a cottage industry with lots of security researchers coming up with new interesting side channel attacks. I mean, we've had, as you can imagine, designing processors, all of the ways you get performance out of modern processors use speculative execution and things that are side channel vulnerable. So there's been a lot of dialogue around how do you design more robust hardware sort of in principle. This is a pan-industry problem of how do I get good performance without creating side channels? It's a really, really hard problem to solve. So we've been working on, every time there's a new iteration of side channel, we have new mitigations that come out, and it sort of goes on and on and on. So I think that will continue as people find new vulnerabilities, we'll find new mitigations, and it's sort of like all the security issues. One of the interesting things I would say is, for as much attention as the side channels have gotten, they're actually quite hard to exploit in general. If you look at some of the other exploits that are around, generally are way, way easier to exploit than side channels. Not to say, I mean, we spent a lot of time mitigating them, but they are actually in general pretty hard to exploit. But nevertheless, there is that isolation that separates the trusted and non-trusted, helps you if you're attacked on the non-trusted side, I guess would be the summary. So that's sort of the gist of it. With our Xeon, starting in the Xeon 5th generation, we have the TDX capability. So Emerald Rapids, which is Xeon 5, which is out in the market now, has this hardware capability in it. It was in the previous generation, Sapphire Rapids, which is at Azure and Google Cloud and Alibaba. They have this in either GA or early preview in the CSP context on the previous generation hardware. And now with Emerald Rapids, it's on every Emerald Rapids. So this hardware exists. If you have an Emerald Rapids generation forward platform, the TDX capability is there in the silicon. So now we're working on getting all the software enabling done across the ecosystem. And this is just another sort of, before I show that, where we're at in enabling it. This was SGX. This was more of an application level secure guard extension. So it really is at the top level here where you have a secure enclave and you run your application. You do have to modify the application to use SGX or use a library OS. So it's more invasive in terms of the software changes you have to make at an application level. And you're really putting the trust boundary just here. Versus TDX, it's the entire, everything inside of this box is trusted. So the guest OS, your application, your data, you don't trust anything down here. That's what the trust boundary is implying. So you don't have to trust the hypervisor, the host OS, whether it's on a CSP or on your local edge device or enterprise device. And the other thing that goes along with both of these is attestation. How do I prove that what I have is the right versions and it hasn't been tampered with? So we have launched an attestation service called Intel Tiber Trust Service. It used to be called Intel Trust Authority and used to be called Intel Amber. So it's kind of gone through its name progression. So this is something that can do attestation for both SGX and TDX. And we're working to get this integrated with SUSE as an attestation option. You don't have to use this service if you want to use something else, if you have your own, but it's an option for attestation. The TDX support, there's guest OS support, so this actually has to be modified for TDX. So the guest OS has to be enlightened to be aware of TDX because there's some slight changes in the kernel of the guest OS. That's been around for a while, and I'll show you the specific versions in a minute. And then the host support, so that's this part of the stack, also has to be aware of TDX. That's in preview. So guest OS, if you want to run in a CSP, you can use SUSE Linux. It's in production. If you want to run on Azure or Google or wherever, Google Cloud. If you want to run a whole TDX system, including the host, that's currently in preview, and we're working towards an SP6-based production release, hopefully. We're doing some planning with the SUSE folks on that. SGX has been supported for a while, so if you're using that or interested in that, it's been in the roadmap and the platform for a long time, and that's in full production at this point. Any questions on confidential compute before we click ahead to AI? So very similarly on AI, the work is foundationally around making sure all of the accelerated capabilities are supported. So we have a number of accelerators in the CPU themselves. So we have AVX 512 and VNNI are instruction sets that help accelerate AI operations. AMX or advanced matrix extensions, even more so, and that showed up in Xeon 4th generation forward. So that does, especially for inferencing on the CPU, it can give you 4 or 5x better inferencing performance. So it really suitable for, not the gigantic models, but 70 billion parameter models. You can do inferencing. The Google Cloud folks did a really nice talk at their most recent cloud conference about, for a lot of people, inferencing on the Xeon is fine. Like, you don't necessarily need a GPU to do significant inferencing, and it's available everywhere. I mean, the beauty of the CPU inferencing is it's on every instance. In Google Cloud's example, it's really easy to get. So, it can be an attractive option. We also have GPUs that are supported. We have our data center Flex in particular. Discrete GPUs that are supported, and then we have a new family of AI accelerators. So we just announced Gaudi 3, which is a purpose-built AI accelerator, data center class AI accelerator. Gaudi 2 has been out, not widely deployed, but Gaudi 3 is going to be very widely deployed, supported by all the OEMs, coming second half of this year into the market, and we're working with SUSE to get that fully supported in their SUSE AI stack. So there'll be more to say about exact timing of when we'll have all of that lined up. But that's kind of the current work in progress for us in the AI space is Gaudi 3 in particular, which is very competitive. We announced our pricing for that actually at Computex a couple of weeks ago. So if you're interested in what does it look like against the NVIDIA offerings, we put out a bunch of details on how it's going to be priced and performance benchmarks. And as I said, working with the SUSE folks to get that fully supported so you can run their AI stack on top of Gaudi 3. So that's something we're very actively working on.
Before you move on,
yes.
Maybe it's worth mentioning IDC.
Yes. Yeah. So we launched this maybe a year and a half ago. So it's Intel Developer Cloud, which is a place where you can get access to the latest, greatest hardware. So we're building large Gaudi clusters in the Dev Cloud. So this is like a sort of a boutique CSP offering, if you will. It's not really meant to be a full-blown CSP place, but really more a place for developers to come and get experience with our latest hardware. So if you're interested in, the Gaudi line, especially the way you could get early access to it would be in the Dev Cloud, and we have we can give you more info if you're interested on how to get access. But we'll be building a fair amount of capacity of Gaudi 3. So if you wanted to try out, a pre-release of the SUSE AI stack on a Gaudi 3, on a latest Xeon, you could get access to those systems and kick the tires, essentially, to see if it suits your needs. So that's a great way to get, obviously, getting people physical access and shipping boards and all of that is sort of yesterday's way of doing hardware access. So this is all hosted in the cloud. Anything else to add on AI, Christian, before I go on? All right. So that's kind of the summary of what we're up to with SUSE. As I said, we're working really hard. We have meetings every other week with the engineering teams, aligning our roadmaps and working through issues and fixing bugs. And it's been a very good, productive partnership, ultimately resulting in, if you're a SUSE customer, getting great access and support for our latest platforms in SUSE Linux and Rancher and their product portfolio. We do a lot of joint testing work as well to make sure that everything works really well out of the box. Ideally, as soon as we launch hardware or they launch a new product, things fit together and you sort of get the experience you expect. So that's all I've got. Thank you very much.